All right, this video is on um, covalent bonding and on bond polarity and electronegativity. There's a lot of different things we're going to be talking about in this video. So let's go ahead and do a quick rundown. Uh, polar, or not polar, but covalent bonding, that's when electrons are going to be shared between atoms. Now, we already talked about ionic bonding, which is when electrons are going to be transferred. They're either going to be gained or they're going to be lost. Okay, so reminder, if I had, say, sodium, which has one valence electron there, and I had fluorine, which has seven valence electrons there, what's going to happen is in order for the outer shells to be filled, this sodium electron is going to come over here, right, and become uh, part of the fluorine. And so the fluorine gets full, the sodium gets full, and then we end up with a sodium ion and a fluoride ion. And we have an attraction between the two of them, and we call that attraction an ionic bond, right? Now, ionic bonds are between metals and nonmetals, okay? When it comes to covalent bonding, when the electrons are shared, this is going to be happening between um, nonmetals, and we'll get to that in time. So let's go ahead and move on to the next slide. What I want you guys to realize is the ability for you guys to do a Lewis structure is going to be huge in this part of the unit. Okay, so if you remember, a Lewis structure is a symbol. Let's go ahead and take calcium, right? And I need to look at the number of valence electrons on calcium by looking at the periodic table, and I see that it has two because it's an alkali earth metal, and all alkali earth metals have two valence electrons. And like I said, I can normally just count across the columns of the main group elements and count. So one, two. So that's my Lewis structure, or my electron dot structure for calcium. Now, when it comes to nonmetals, such as, say, hydrogen, right? Hydrogen is in the alkali family, even though it's not really an alkali metal, but it has one valence electron, so I'm going to put that one valence electron there. Now, if we look, hydrogen is one of those elements that um, it's happy with two in its outer shell because its outer shell is the first shell. Just like helium and lithium and beryllium and boron, they're more than willing to only have two, which would still be an outer shell filled for them. Okay, so when it comes to hydrogen, hydrogen can do one of two things. One, it can gain an electron or it can lose an electron to form an ion. But when it comes to like hydrogen gas, okay, which is H2, okay, obviously uh, no ions were formed here. Okay, this is just a molecule of O2. You're thinking, well, what's a molecule? A molecule is um, similar to like when we talk about compounds. A compound is when you have a collection of atoms from different elements. Okay, a molecule is when you have a collection of different atoms, or even the same atoms that are physically bonded together. Okay, we have not seen any molecules yet in this unit. All we've seen are compounds because the aforementioned um, ionic bond is not a physical connection between two atoms. They're just an attraction between two atoms. So I'm going to symbolize another hydrogen here, which also has a valence electron. And if you remember, like I said, hydrogen is one of those elements that'd be fine with two. Okay. Now, what's gonna happen here is this electron for this hydrogen and this electron for this hydrogen are moving around, right? They're moving around in a whole bunch of different places, you know, going in a lot of different movements and having spin and all that kind of fun stuff. But what you guys need to realize is that at any point, sometimes that electron might be right here, and then this electron right here might be right there. When they are in a pretty close proximity to each other, they'll actually go into the other atom's orbitals. So all of a sudden, this electron right here that's a part of this atom may actually end up over in the other hydrogen's atom atomic orbitals. And what's happening right there is they essentially these two atoms of hydrogen are sharing their electrons. and we call the sharing of electrons a covalent bond. And I'm going to indicate a covalent bond with a line, like so. Okay, so this right here would be hydrogen gas, or what we call diatomic hydrogen, di meaning two. Okay, so let's take a look at another more common, I know it's not common because hydrogen is the most abundant substance in the universe, but at least one that is a little more important to us is water, right? So let's go ahead and take a look at water. Um, you guys all know the formula H2O, which means it has two hydrogens and one oxygen. So, well, the first thing you're going to need to be able to do is um, do the Lewis structures for each atom and then bring all those atoms together to form a Lewis structure of the entire molecule. So, here I have oxygen, which has 1, 2, 3, 4, 5, 6 valence electrons. And I have hydrogen, right, which we know what hydrogen looks like, and we know that there's another hydrogen. So there's my Lewis structures, or my electron dot structures, for each of the three atoms that are in that molecule. Now, the question is, how can I arrange those? And I'm going to go ahead and change this just so the hydrogen turns out to be a little, let's go with oxygen. Oxygen's usually red. Okay, and we'll go hydrogen being black. Okay, so is there a way that I can arrange all of these atoms where everybody's happy? Okay, now if you remember, hydrogen, helium, beryllium, lithium, boron, they can combine and be happy with just two electrons. Okay, oxygen wants to have 8 in its outer shell to be happy. All right, so I'm going to redraw the oxygen right here, make it a little bigger, right? And then my hydrogens, right? Each hydrogen has one valence electron that's ready to be shared, and the oxygens each have two valence electrons that want to be shared. So as it turns out, the orientation will be this hydrogen will be here, and this hydrogen will be here. Why does it go there? The reason why it goes there is because these single electrons, like I mentioned right here, those are what we call unshared electrons. Okay. Now you're thinking, well, these are unshared electrons too. They're not being shared with anything. True, but they're pairs. And when they're already in pairs, they tend not to form bonds. When they're singles, when they're all by themselves, that's when they tend to form bonds. Okay. So as I look right here, remember I said those electrons are moving around, and there's times when the electrons will be, they can actually go into another atom's orbitals. So these hydrogen atoms will maybe go in the oxygen, and the oxygen electron may go into the hydrogens. Okay, but either way, if you look at the number of electrons that are exposed to the hydrogen, is hydrogen happy? And the answer is yes, because it has 1, 2 electrons. What about this one? Is that hydrogen happy? It is, because it has 1, 2 electrons. Does it matter that one of the electrons is coming from a different atom? No, because electrons are electrons. That's how they view it. Okay, looking at oxygen, how many electrons does it have? It has 2, 4, 6, 8. So is oxygen happy? Yeah, oxygen is happy too. And like I said, whenever you have these shared pairs of electrons, you indicate them in the Lewis structure as a line. So if I was to draw the Lewis structure for water, it would look like this, right? And every single line represents 2 electrons. So if you're ever looking at a Lewis structure and you're wondering, well, is everybody happy? Because you're going to have to do Lewis structures. I am going to make sure that you know how to do that. So if you don't check your work, you may not get your Lewis structure right. And the best way to check your work is to simply count the electrons. Okay, hydrogen. I know hydrogen only wants 2, it's fine with 2 electrons. So hey, there's 2 electrons right there in that line. It's happy. Hydrogen there on this, so this hydrogen, check. This hydrogen down here, also check. It has 2 electrons in that line. Oxygen, right? 2, 4, 6, 8 electrons. Oxygen's happy, so this is your water for you. Okay? Now, I'm going to go ahead and do a couple more examples. All right, let's take a look at um, ammonia. Right, this is going to be a common compound that we're going to see a lot. Remember, I'm going to say compound, but this is also a molecule. Okay, compounds like water and compounds like ammonia, those are also molecules because I'm actually going to link them together. The atoms are going to be linked together by bonds. Okay, if this was, say, potassium chloride, where I have a metal and a non-metal, okay, those aren't actual physical connections between the two of them, so I cannot call that a molecule, but it is still a compound because it's composed of more than one type of atom. Okay, and that's the other thing you notice. Potassium chloride, that's a metal and a non-metal, right? Um, lithium nitrate, that's a metal and some non-metals. Here, nitrogen and hydrogen, that's only non-metals. Water, that's only non-metals. Okay, so I'm gonna look at nitrogen. Let's go ahead and make nitrogen blue. Why not? There's my Lewis structure, or for nitrogen, electron dot structure. Okay, each hydrogen, there's three of them, right? I went ahead and put them just on the side because I'm sure you guys can see the connection here. These hydrogens are going to arrange themselves around this nitrogen to be able to share electrons with the nitrogen. And every single shared pair of electrons, okay, is going to eventually form a bond, right? So I'm going to have a bond, 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 hydrogen, hydrogen, hydrogen. Okay? Now, is everybody happy? Let's take a look. Hydrogen is happy with 2. Does it have 2? Yes, because there's 2 in that bond. Same thing with the bottom hydrogen, the left hydrogen, the right hydrogen, whatever hydrogen you're looking at. If it has 2 electrons, it's happy. Now, looking at the nitrogen, right? Each nitrogen needs to have 8 electrons to be happy. Does it have 8? And the answer is yes, because there's 2 in that bond, there's 2 in that bond, there's 2 in that bond, and then it has its unshared pair for a grand total of 8. So nitrogen's happy. Okay, so that is ammonia. Looking at yet another example, okay, um, oxygen gas, right? Some important stuff that we breathe, right? It's 2 oxygen molecules, or 2 oxygen atoms. Now, is this a molecule? Yes, it is, because it's going to be connected by bonds. Okay, is it a compound? No, it is not, because it's only made of one type of element. Okay, compounds are when more than one type of element come together in one way, shape, or form. Okay, this is only made of one type of element. So there's my oxygen Lewis structures right here, right? Well, if you look, how is each one of these guys going to get um, their full outer shell? I'm going to go ahead and move this around here. Okay. Now, you've heard of this and you've seen these before. Okay. This, if I was to share, these electrons right here, this would be my Lewis structure. It would be oxygen, and a bond. Okay, well, obviously, I have my bond there, I'm done. Okay, hopefully you realize that that doesn't look right, because if I was to count my electrons, each oxygen only has 7. And 7's not happy, 8's happy. So as it turns out, um, the oxygen will actually share more than one pair of electrons. And like I said, you've seen those before, they're called double bonds. Okay? So now if you count the number of electrons in each oxygen, right? This oxygen right here has 2, 4, 6, 8. And this oxygen right here has 2, 4, 6, 8. So this is how a double bond is going to form. Okay? Oxygen is quite notorious for forming double bonds, so you're going to definitely want to keep track of that. Doesn't mean it's always going to form double bonds like we saw in water, but oxygen does tend to form double bonds a lot. All right? Let's go ahead and look at one more example, and that is nitrogen gas. Okay, the most abundant gas that's in our atmosphere. All right? if I was to draw the Lewis structure, which you guys should be able to do, hopefully in your sleep, by the time this unit's over, okay? Here I have my two nitrogens, all right? So let's start pairing up these electrons. Oh, here's a pair, right? Well, if I did that, that would be here, 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 there, right? Hopefully we see that can't work because nitrogen, each nitrogen only has, what, 2, 4, 5, 6 electrons. That's not going to work, okay? So maybe they'll pair up again. So I'm going to end up with nitrogen, a double bond, right? Now we're getting somewhere. But if I have a double bond and each bond is representing 2 electrons, if I count those up, 2, 4, 6, 7, I only have 7 electrons, right? So as it turns out, somebody is going to share yet a third pair of electrons, and I'm going to end up with this, a triple bond, okay? And if you count the electrons, nitrogen is happy in this case because nitrogen is one of those elements that likes to have 8 electrons, okay? So 2, 4, 6, 8, 2, 4, 6, 8. So nitrogen's happy there. Now, one concept that you guys need to be familiar with when it comes to these bonds that form is, yeah, these electrons are being shared, but you need to understand that they're not shared equally, okay? Some of these elements are hogs. They like to hog up all the electrons in a molecule, okay? The wonderful example that we're very glad that it does this is hydrogen and oxygen forming water, okay? We know that this bond right here is representing electrons being shared between oxygen and hydrogen. But as it turns out, they're not being shared evenly. The oxygen really likes electrons. So the hydrogens honestly don't really get their 2 electrons very often, but they're getting them enough to kind of stick around, okay? And the idea that electrons being shared unevenly is called polarity. All right? When something is polar, it's telling, like if a bond is polar, it's saying that within that bond, the electrons are not being shared evenly. Okay? Now, how are you to determine if a bond is polar or not has to do with, here's another one, it's electronegativity. Okay? The electronegativity, which ranges from 0 to 4, okay, is indicating how much it likes, how much a specific element likes electrons when it's in a bond. Okay, obviously atoms that are smaller, right, the ones that have the electrons and the valence electrons closer to the nucleus, tend to have higher electronegativities than those that don't. Okay, for example, if I was to compare nitrogen, oxygen, and fluorine, which is the second period, right? I know that nitrogen is, so this is going along the second period, I know that nitrogen is larger than oxygen is larger than fluorine. Well, as it turns out, when I look at their electronegativity values, which is in your book, okay, nitrogen's 3.0, oxygen's 3.5, and fluorine's 4. Fluorine is by far the most electronegative atom there is. Okay, so it makes sense that as my atoms get smaller, the electronegativity would be increasing because those electrons are closer to the nucleus, which means they're going to be pulling on those electrons even more. Okay, as I go down a group, okay, let's go ahead and take fluorine, chlorine, and bromine. Okay, they all happen to only have 1 valence electron or 7 valence electrons, so they're going to really want that electron. But as I go down a group, okay, my electronegativities are going to decrease. Okay, so the trend that you should see right here is electronegativity, which I'll tend to abbreviate like so, Electronegativity is going to increase as you go to the left or to the right, and it's going to increase as you go up, right? If you notice, this trend on the periodic table is very similar to ionization energy, right? It's the same trend, right? Ionization energy, and it's also the opposite of the atomic size or atomic radius, which, like I said, when describing the electronegativity, that would make sense because larger atoms would tend to have less electronegativity. All right? Now, that's what electronegativity is. How do I know if it's an actual polar bond or not? All right? And the truth is, it comes down to just the difference in the electronegativity values. All right? So, I know this is a long one, okay? But we've got about 5 minutes left. So, let's go ahead and show you the way to figure out if a bond's polar or not. So let's choose a couple bonds. Let's go ahead and choose a carbon-hydrogen bond. Let's choose a hydrogen-hydrogen bond. Oops, that's not a hydrogen, that's a carbon. A hydrogen-hydrogen bond, and say a hydrogen-fluorine bond. Okay? And then just for the fun of it, why not a lithium and fluorine bond, which of course you should be going, well, there's no bond there. You're right, there is no bond. We're just going to go ahead and show little dots to indicate the attraction there, okay, which would really be, right? So, when it comes to determining if a bond is polar or not, you need to get the difference, the mathematical difference between the electronegativity values, all right? So as it turns out, carbon has electronegativity value of 2.5. Hydrogen has electronegativity value of, it's ugly, 2.1. Fluorine, like we saw, was 4.0. Okay, and lithium is 1. Okay, 1.0. So let's go ahead and take a look at the differences between these electronegativity values and see how I'm going to classify them. Okay, so carbon-hydrogen, carbon would be 2.5 minus 2.1, and that difference is 0.4. That's my difference. You're thinking, well, what does that mean? That's just a number. Here's your scale. If it is 0.5 or greater, but not greater than 1.9, you can indicate that that bond is a polar covalent bond. Okay? So, looking at carbon and hydrogen, 0.4. 0.4 is less than 0.5, therefore this would be a non-polar covalent bond. Okay? Take a look at hydrogen minus hydrogen. Hopefully we can figure this one out. 2.1 minus 2.1, that's 0. Okay, again, that would be less than 0.5, so this would also be non-polar. Hydrogen and fluorine, all right? So fluorine is 4.0. Carbon is, or excuse me, hydrogen. Hydrogen is 2.1, right? 2.1 difference there, we have 1.9 as our difference. Well, 1.9, if it's equal to or less than 1.9, but greater than 0.5, then that is a polar covalent bond. So this is polar covalent bond. Okay? Now, let's take a look at this lithium fluoride. This is an actual ionic bond here. So I'm going to take 4.0 minus 1.0, and my answer here is 3.0. Right? If I have anything that is 2.0 or higher, that's ionic. Okay? It's pretty simple. Now, if you come across anything that, you're like, oh, it's a metal and a non-metal, but it's not an ionic attraction, or it's not ionic according to the electronegativities, understand that the fact that it's metal and non-metal automatically make it ionic. Okay, it's just, think of something being covalent or something being polar covalent or non-polar covalent as a character of the bond, meaning that the closer you get to the closer you get to 2, right, the more polar, or the closer you get to 2, the more ionic character you get. The farther away you get from 2, the less polar or the less ionic character you get. Okay, but this right here, okay, very important right here. Make sure you write that down. Write that number down. 0.5 greater than or equal to, um, or less than or equal to 1.9. That's your indicator if it's going to be a polar covalent bond or not. Okay. So, if you guys have any questions, by all means ask.